question with the result I got. You see my screen? Oh, okay.
Okay.
Yeah. This is the two well that locate on Central Basin platform. Yeah, and I got the result here.
Okay.
This is the plot that showing the TCMR. Yeah, look, you see here. And I got a problem with well number 47. This two well is offset well, right? But in Newton of well 47 is different. It's high Newton here. Yeah, at Burnett zone. Yeah.
Well, for the platform well, I think the issue with the computations, matching the TCMR. If you look at that bottom section, that Woodford Shale, right?
Woodford Shale.
Yeah.
You've got a lot of dolomite in that model.
Yes.
And when you put a dense mineral in, right, the only thing that it can do to compensate is add porosity to match the grain density. So that's what's happening, right, is that you've got all that dolomite. It's a symptom of the disease that's wrong with your interpretation, that you end up with the higher porosity in the Woodford. Now, what I would do is split that Woodford interval in your clay interpretation in half, because the upper part of the Woodford generally has a different type of clay and a different clay endpoint than the bottom part. So for the bottom part, you'd have a high clay density, right? Because usually that's like a 2.7 or something clay density, say, for that lower half. The upper half is going to have a lighter clay density. When you put the lighter clay density in there and then rerun the clay parameters thing and then rerun mineral solver, it's going to drop your porosity and it's going to remove some of the dolomite from that model.
Got it.
For the upper section, it's probably a similar story, right? You've got high porosity as compared to the NMR. And if you look at your model, it's throwing quartz in. Okay. And we don't know, what the mineralogy is. And the lower Barnett Shale does have some silty components in it. So it's quite likely that you do have some quartz there. The dolomite that's showing up in the upper section is probably incorrect. That may be a function of the log. So it looks like you've got flatline resistivity and some other things happening up there. But I think your clay volume is off. And I would imagine that your clay endpoints are probably off too. And you may need to break those sections up. That bottom part, you can see what the density does. The density, everything sort of drifts lower density in the Barnett section, right? And when that happens, look at what happens in your model. Your porosity starts to increase. Right? This is the basic petrophysics without doing petrophysics. Density goes down, porosity goes up. Why? Because there's, that's the mental model. That's the physics-based model of what a rock is. Right? It's got matrix and it's got holes. Bulk density measures both matrix and holes. So if you've got more holes, bulk density goes down. Done. Right? And that's exactly what's happening here. The CMR data is flat. So that's telling us that something is adding porosity to that lower section that should be there potentially if the CMR is right, which we believe it is because there's not a whole lot of caliper problems in that hole, right? So
Yes.
that tells me that maybe the clay volumes are too high or the endpoints for the clays are wrong. And that's why you've got, or the TOC could be wrong as well. Remember, we use the vitrinite reflectance with depth trend for the TOC properties, right? And because you're on the Central Basin Platform, it's much shallower, things are different. What's the thermal maturity, right? You could change the density of the TOC in that interval too to change the porosity. You can mess around with some of that to see how much it impacts the result.
Okay.
That's my take on that. On the other well, the number 42 or whatever it is, that looks like I can't really read the top set well, but it looks like the bottom one is the Barnett, right?
Yes.
Yeah. So same sort of thing, right? You've got a bunch of dolomite in that model. And it looks like there's washouts in there and the caliper and D-row curve, so that the total CMR porosity is probably not quite correct. And, you know, all things being equal, you know, there's not a whole lot of log there. So, you know, I would just, again, use that dolomite as a flagging indicator to you that something's wrong with your density. Your mineral densities in your model are messed up somewhere because it's unlikely that that dolomite is there.
Mm-hmm.
So when the dolomite
Okay.
goes away, you probably have an interpretation that's closer to reality.
Okay. I'll fix that.
Tube, do you want to pull open that
Yeah.
yeah, so you need, yeah, all it's doing is he's putting values in there to match the data, right? So change your high bound to like 700, put 700 in. You see what it did? It just pushed the curve up. Yeah, so all he's doing is he's matching those red data points. That's the raw data, right? So he put 450 in there or whatever because it matches the higher values of the ISIPs for the high bound. So put 400 back in there, for example, for the high bound. You see now it's clipping the top of those data points. Now this isn't magic, right? It's just fitting the data is all it's doing. Well, that's what we're doing is we're reverse engineering here, right? We've got the data, and then we're fitting a model to the data. That's what we're doing. And so we recorded the ISIPs, and we've got a stage-to-stage interference and all that stuff, and we're fixing these parameters in this physics-based model, analytical model, based off of Sneddon, to infer what's happening with the data. Like I said, if I did this, it would literally take me 30 seconds. I just load the data in there, punch a couple numbers in there to fit the data, and I'm done. Right? Like we're not there's nothing else to do. So yeah, so what, like I said, what the guy did, David Jenkins, is he programmed it up so that it does a numerical fit as well. You know, so that it tells you, like, if I try to minimize, if I do a minimization problem and I try to get a best fit, what does that look like? That's that black dash curve. Yeah. So we've only got 22 stages for one well, so all we have to do is cut and paste the ISIPs in there, and then enter the information about the well, right? Like what's the stage spacing, all that stuff, the depth. Yeah, so like this is noisy data also. So sometimes we have to cull noisy data, but you know, like the noisy data is kind of affecting the numerical minimization thing. That's why you get this really weird looking black dash line. What I would probably do is you've got those stages like around whatever that is, 13 to 18. The values are very low. Yeah. Right. And you know, like, do we have zero net pressure? How is that even possible? Right? That doesn't make any sense. There's something wrong there. I think we need to look at those ISIP interpretations. In particular, stages 16 and 17 are extremely low. So, yeah, like what's the, where in here do we insert the minimum horizontal stress? So, yeah, it's right up. Go to the top. Scroll over to the right. There, it says SH min 1.00, 1.09. So it's getting that from the depth. Like, what's the calculation formula for that again? Put your SH min. If you go back to SH min at 1.00 is extremely high. It shouldn't be that high. So that's a function of one. Yeah, so the initial ISIP thing, it says adjust initial ISIP set to the value of the first ISIP. That's what it is, right? Stage one. Yeah. So the idea is that the ISIPs technically should increase, right? But we've actually got some that are lower than that, which is why we end up with that problem. I don't know that I like what he did with that. This is not my spreadsheet, right? This is Jenkins' spreadsheet. And that's, we also need to look at the PDF file and see how those ISIPs were picked and stuff, right? Like, it may be wrong where they picked that. Or it could just be that, you know, we got out of zone with the geosteering. I think I don't know if I forwarded that to you or not, geosteering for the well. But we can look at that, right, and see where it's in zone and out of zone and stuff like that. You know, if there's anything going on with the wellbore trajectory, because this is a conventional reservoir, and that may tell us something too. We saw this like a long time ago. I did a bunch of work with the same guy, Doug, when I was in Egypt. And we drilled the first unconventional horizontal wells in Egypt. It's Apollonia chalk. And I was in charge of the core analysis, the cracked stuff on the technicals. Well, or something about the same millidarcy permeability, about 1 millidarcy, half a millidarcy, and about 4,000 feet deep, so pretty shallow, low stress, right? But in Egypt, there's a lot of faulting, and this well cross-cut a bunch of faults. So we compared the data that we saw, just like this, identical. We were comparing these ISIP values from stage to stage to see how they were changing along the lateral of the well. And what we saw was, when you get close to the faults, there was like this same thing, this rubber band and snapping effect, where you've got stress build up and then it breaks. You get to the other side of the fault, you're in a different regime. SH-min looks different, ISIPs look different. So that's what I wanted to look at here, is to see how much variability we have in the reservoir over the length of the lateral. How did it treat? We had higher permeability zones in some of those stages that have, why do we have lower ISIPs, for example? Is there something that happened geologically that we encountered different rock when we fracked it? And we wound up with those lower values, or was it just really shitty interpretation of the surface data by the CUD team, or whoever filled out that spreadsheet? Oftentimes, what first of all, is it a downhole ISIP? Is it a surface ISIP? Trying to take friction out of it. Can you hear me? PNP, can you not hear me?
Yeah.
But
You can or
too
can
bad.
Can't. ไม่ได้ยิน
you can't hear me.
Yeah.
I don't know. What about now? Better?
Yeah. Again, please. อ้าวไปละ
Just better?
Yep.
The same? I don't know what the hell
Better.
happened. I had bad connection or something. The whole point of this is to look at, understand whether or not we're, these values are interpreted or not. Are they just calling the ISIP the instantaneous pressure when they shut the pumps off at surface, or is there a friction component that you're trying to analyze right down hole for the slope analysis? If so, you can get very different values depending on who analyzes that data. And so when we were looking at the DFITs, for example, we do everything with a bottom hole pressure. And in order for that to work, we have to take out friction. And even after you shut the pumps off, there's still transient friction. So you have to do a slope fitting exercise to get the ISIP properly. These, I assume, were picked off of surface pressures that end up pumping. But we have to verify that, make sure that they're correct. Overall, your blue curve there, right, is the answer that I would present to the client. So we've got a high bound and a low bound. If you look at the fits, right? What does it tell you in the top of the table for the heights for those? So it says best fit height manual. Best
สีฟ้า
min fit height and max fit height,
100
right? So you're looking at you know, your best fit, I believe, is your blue curve, right? And then the other two, so that blue box on the top is what we're after. So it's saying at the low end of things, we're 75 feet. On the high end of things, we're 200 feet, and the manual in between, the average is about 145. So, you know, if you look at the logs in those PowerPoints that I sent you, you know, and you look at that that reservoir interval, you know, how many feet thick is it, right? Like from the upper lobe to the lower lobe. So we're looking at 75 to 200 with an average of 150. So open that thing up. This will work. I'm just looking for logs, right? I want to look at the logs. Find a slide with logs on it. I go back, and that's that geosteering I was telling you about too, right? Like we should map everything out on there. So what's the height then? I can't read that. It's really small. It's like 9,000 feet. What's that bottom one at the very bottom? That second zone that's highlighted with the green box around it. What's the depth of that thing? No. The 9,000 for the top one. What's the bottom? 9,200. I think it's 9,200. We just our heights that came out of our model were between 75 feet and 200.
Oh, we lost you again.
What does that tell you?
Your sound
Yeah.
disappear.
What
What's
about
wrong
now?
with your microphone?
Better?
Okay,
I
better.
don't know. Better?
You keep talking. Okay.
Yeah. So, you know, like I was saying, our model said anywhere between 75 to 200 feet. Okay. Now, with what we just said, first of all, if you look at this slide, it tells you a lot of really useful information to what we observed in that spreadsheet. The net pressures were very low for those stages, right, that were like 15, 16, 17, whatever. Those indicated that we had a small height, like 75 feet or something. Okay. And we had a low net pressure. Now, if you look at the logs, where is the zone of lowest net pressure? Or the lowest, where would it be the low, where would the net pressure be the lowest? Like, so our ISIP is really low, right, in those zones. So where would that be? Going to be in the lower low, okay, because that's where that.
Keep talking.
Now, what about now? Can you hear me now?
Yes, it's good.
Hold on a second. about this?
No.
It's not better. What about now? Is this better?
Better.
Yeah.
I don't know what the fuck's. Anyways, my whole point is that's where the stress is low, right? So you have a low ISIP there, you'd have low net pressure if you were in that lower zone. Okay. In the up, so what makes that zone have a low stress? What makes it have a low stress is its high porosity. If you've got a high porosity, okay, in one of these reservoirs, you have more fluid, you have less matrix, it's more compressible, and you end up with a lower overall stress gradient. That sort of scales with porosity. So if I were making that plot that you've got in your spreadsheet of your ISIPs versus stage or whatever, those ones that are really low, 15, 16, 17, whatever it is, I would expect that those are going to be high porosity potential. Okay. Now, if you go to the screen, to the slide that's got the geosteering interpretation. So we need to identify which stages are which on this, and see if we have to get some more information, I think, but we need to figure out what's going on laterally along the length of the well, to see if that correlates to anything, right? That we see that in a different zone or something. Is this better? Better now? 1, 2, 3. I think my
Okay.
headphones are dying.
Okay.
Yeah, I think the cable's like done or something. It's been bent enough times that the microphone is shot. So anyways, you need to do some detective work, figure out if that coordinates well or not. The other thing I would expect to see is that if you pulled the treating plots from the CUD report for those stages, let's look at the slope behavior, the Nolte-Smith plots, I sent you that, right? I sent you that CUD report. The PDF file that's got the full from CUD. They're the guys that they pump the fracs on this well. Yeah. Open it up. Yeah, so find the stages, whatever those were, 15 or 16, right? That yeah, there's one of them, right? Like we need to compare these to the other stages to see why the ISIPs are so low, and to see if there's any change in treating behavior, right? Is the slope different? Was there anything different about the job on that particular stage? Pump at a higher rate, break down easier? Was it harder to break down? What's going on, right? From a completions, frac standpoint, what's happening with data analysis? Yeah, let's look at stage 16, 17. I think those are, I eyeballed those, they look like they were the low ISIP stages. Keep going. Look for a Nolte-Smith plot, right? There you go. Yeah, I mean, you've got your well pressure, right, which I assume that's surface pressure. I don't, or maybe not. Downhole converted pressure. I don't know how they're getting that. We need to figure that out. You got your pump rate, 80 barrels a minute. Right? They ramped up rate. Pressure went with it. Treated negative slope the entire time. Right? Their ISIP that they picked. Again, that's where I'm getting confused here because these plots, they're showing a computed downhole pressure. It's like, who knows how they're computing that. See if you can find the surface pressure measurements. Yeah, it's that downhole that they're calculating. That's a chemical plot, right? That they're showing the concentrations of the different chemical additives. Yeah, I hate when vendors do these things because they don't have a pressure gauge, right? So they're just calculating the shit, but they're not telling you how they're doing friction correlations or how they're applying the head, stuff like that, right? So, you know, yeah, because we don't have apples to apples comparison, we're going to have to look at these stages, just compare them in the same metrics that they're using, the swell side pressure, compare it back to the stages that have a high ISIP, and just try to understand what's going on. Like I said, everything should track. Really what we need to do is we need to get all of this information into one place that we can plot it all. Right? We want to plot that horizontal well length versus a geologic geosteering interpretation to see what it's cutting. Right? We got to look at that gamma ray because that's probably all we have to work with. And then need to plot the ISIPs on top of that. And we need to plot, you know, the other metrics that we have, slope treating analysis, something to indicate what's going on and see if it tells a story. That's what we're trying to do, is integrate all of this data together to see, why do we have those low ISIPs? Did we encounter higher porosity rock? Does the interpretation support that? Yes or no? Right. And then our escalation model, if we look at that, we say, you know, we've got anywhere between 75 to 200 feet with an average of 150. We also need to go back to those fracture models that we ran. We need to look at the height from the stim plant and understand, you know, based off what we pumped. So we don't care about the 60 barrel a minute case. We're going to look at the 80 barrel a minute 4 cluster models. That's what we pumped. And we're going to see what the geometry looks like in those compared to what we're seeing from the secondary independent measurement of height. And understanding that it's an average. So that's what we're doing with all this. That's why we're. And our SH min and SH max and stuff, I need to talk to Jenkins about that because those values that are posted are like overburdened. They're not minimum horizontal stress. Right? But anyways, yeah, well, normally we take the lowest value out of the entire data set, and that's what we use as the initial ISIP. Yeah, right. Yeah, otherwise you have a negative net pressure for some of the stages, right? Yeah, I mean, so scroll back up, yeah, to that plot with all the dots on it and the lines and stuff. So I mean, like, if the way that I interpret this is that for the first couple of stages, you actually start to build stress shadow, right? It escalates up and it starts to oscillate around that boundary, the high boundary, right? Which is whatever that is, 200 foot, right? And then something happens where you drop, right? And then you go back up again, and then you drop, and you go back up again. So it's having a hard time maintaining stress shadow. And the only way for that to happen to make sense to me is that reservoir is changing along your wellbore path, peering in and out of different layers of rock. And you're cracking different parts of the reservoir as you go along. You're hitting the higher permeability stuff, higher porosity stuff when it starts to drop, right? Or there's faulting or something else, fracturing going. It's resetting your stress state. So it's interesting stuff to try to decouple this. You need more information, but this is what we do. We're like Conan, like the detective. We have to constantly work with whatever information that we have to come up with best hypothesis of what we think happened. Ultimately, the more data points or the more models and stuff that we have that points, the same answer, then we start to believe that answer. So, we need to go back and look at those frac models, see what the height was. We got this Sneddon model. We look at what the height is, right? Is there any agreement? Do they agree or not? Do they agree or not? Right? Between the frac model and the Sneddon model, are they the same or are they not the same? We need to know that.
Mhm. For the next step opinions, we will apply interpretation to remaining wells. We will wrap up those slides to you on Thursday.
Yeah. So
Yeah, as we can.
tomorrow I'm flying. Maybe,
Oh.
I don't know. I feel
Okay.
like absolute shit today. I'm sick because I didn't sleep because of fucking school. Right? They had a 7:30 this morning. They started with the drum solo and music and shit.
สายน้ำผึ้ง again.
Yeah, no, I'm fucking done with it. This isn't funny
Oh.
anymore. It's affecting my health. My hair is falling out. I cannot live like this anymore. So I've already told Game, like, that's it. I'm done. I'm not living in that building. These fuckers, right? Every fucking day, there's a concert over there. A fucking concert with live drums and music and everything in the morning. Like, is there any reason for that? There's no fucking reason. There's just not.
Concert in the morning.
There's just no reason for it at all. A school is not a fucking bar, right? This thing is louder than bars in Pattaya, right? Why do you have live music, the drums, and all that shit? It cuts right through the building. There's no way you can even soundproof against it. It's a party there every fucking day of the week, and that's I hate to say these things, but like, come on, guys, right? What kind of country do you live in? Like, schools are for learning. They're not learning live bands. Like, why are you going to school? What's the point to be in there? You might as well just go work at a bar in Pattaya and be done with it. Like, doesn't make any sense. So, this shit needs to end. I'm just gonna have to move again, I guess. I don't know. But I can't continue like this. And what I'm afraid is tomorrow I won't be able to sleep again, and then I have to sit on a fucking airplane for 20 hours with no sleep. You know what that's like? It's not fun. Also, that you know, these fucking idiots can bang their drums at 7:30 in the morning and you know, just doesn't make any
Yes.
sense.
Happen again.
Friday,
Yeah, it's not fun.
Friday, Monday, and today, 3 days in a row.
Oh,
I'm sure it'll be tomorrow too.
Oh,
And I don't know why
They're
it's
back.
just this one
Yeah,
one
they're
school,
back.
because you know, like this other one, sign on hip or whatever, is quiet. It's just this one school that's shitty, really shitty.
yeah, the window didn't help.
No, it goes right through the wall. It's so loud
Oh,
that
Oh.
you can
From the
go
wall.
into
Mhm.
you go into the other bedroom and you can close the doors and windows and everything. You can still hear it, just as loud.
Oh.
And this is I have a spectrogram. I did an analysis of this, right? I'm not stupid, guys. I'm not dumb. I know about fucking acoustics, right? This is 80 decibels of 60 to 100 hertz that's bleeding into my fucking condo that you're never going to block, no matter how many windows you put in.
Hmm.
And it's if it's that loud where I'm at, it's got to be extremely loud on the ground where the students are. So the question becomes, why the fuck do they need to have it that loud? Right? They don't. There's no reason for it. It's louder than the bars in Pattaya,
Yeah, it's time to move.
you know?
Mm.
Absolutely ridiculous that anybody would do that. And like I say, every day of the week, what are they doing? Why are they not learning math and science or reading or something? Why are they outside, all sitting on the ground with bands every day of the week? I don't get
Yeah,
that.
Picken will help you find another condo, right?
I don't know, but like I can't continue like this.
Mhm.
This is it's
Yeah.
literally killing me.
I
right?
see.
It's killing my health. I cannot continue like this. And on top of it, I'm paying all this money, and I was lied to and manipulated by that real estate agent, you know, and everything else. I'm just tired of all of this. So, anyways, there's a petrophysics meeting tomorrow. I'm going to forward it. Who wants to attend that on my behalf?
Petrophysics meeting with
Yeah, with
who?
Diamondback, with Daniel and all those guys. Somebody needs to go to it. Who wants to go?
Me?
That
Okay,
should
you just
be
volunteered
us.
yourself. All right. And then the other thing that I didn't realize also is that May 25th is actually a holiday
Oh.
in the
Mhm.
United
Holiday.
States. It's one of like the 4 holidays that we get per year, not 40 like Thailand. We get 4, and that's one of them. It's Memorial Day, and because of that, the
Memorial.
Diamondback offices will be closed.
Oh.
So unfortunately, I didn't realize that. So what we'll have to do that day is just enjoy Midland, I guess. I don't know. Figure something out when I get there. Maybe we can meet with Pinion if they're open, but I doubt it. They're going to be closed as well.
Oh.
All the week.
So
Wait.
just for Monday, 25th.
Oh,
Oh,
okay.
just for Monday. Okay.
And then
Memorial.
Tuesday, we'll go to Diamondback's office. I don't know where we're going to fit Pinion in. That's going to have to be at some point. We'll figure it out, I guess.
Yeah.
But Monday will be. Then the other thing I mentioned to Game is that you need to get set up with, be easier if you did an eSIM card through Tello because it's cheap, it's like $300.
Yeah.